Dear colleagues, welcome to the video presentation of our paper titled Still Camera Multiview Spectral Optical Flow Imaging for 3D Operating Deflection Shape Identification, published in Mechanical Systems and Signal Processing. To put the proposed method into context, first some background on 3D image-based displacement measurement. Stereo-digital image correlation analysis conventionally begins with image acquisition using a synchronized pair of high-speed cameras. Feature matching is then used to match the positions of physical points of interest in both images. This information is then used to triangulate the 3D position of these points in every image in the sequence. Most often noted limitations of this approach are the relative complexity of the acquisition system and the field of view of such measurements, which is normally limited to a single face of the specimen. Our proposed method, on the other hand, is based on the frequency domain triangulation of small harmonic motion. Utilizing the properties of linearity and time invariance of a vibrating response under stationary excitation, frequency domain images of the observed operating deflection shapes are used to reconstruct the spatial operating deflection shapes of the object in a single frequency domain multiview triangulation step. The main assumptions are linearity and time invariance of the observed structure's response, along with the stationarity of excitation, facilitating single moving camera acquisition of the response without the need for time-synchronized multiview acquisition. The second theoretical principle utilized in this work is the recently proposed spectral optical flow imaging method, which can be used to identify frequency domain operating deflection shapes in digital images. It utilizes illumination of harmonic intensity to perform an analog Fourier integration of the full field displacements over the camera's exposure period. The spectral optical flow imaging method enables image-based measurements of high-frequency vibration, where the measurement frequency is not governed by the frame rate of the imaging system, but rather the harmonic modulation frequency of the illumination source. A still camera can therefore be used for image acquisition, considerably reducing the complexity and cost of the imaging system. The proposed multiview spectral optical flow imaging method therefore uses the spectral optical flow imaging method for measuring deflection shape images in stationary vibration, together with the frequency domain triangulation process to measure 3D operating deflection shapes using a single moving still frame monochrome camera. In our validation experiment, the specimen was a 3-plane cubic shell harmonically excited on an electrodynamic shaker, with the excitation frequency matching that of the controlled illumination source. First, a simple FRF measurement of the object was performed. The spectral optical flow imaging experiment was then repeated multiple times, each time at a different measurement frequency to measure mode shapes as distinct resonant peaks identified in the FRF measurement. Each time, the specimen was rotated to capture 6 different views of the process at each measurement frequency. Image acquisition was performed using a Basler ACE monochrome camera at 12-bit depth and a resolution of approximately 4000 by 3000 pixels with a global electronic shutter controlled by an external trigger to achieve the required synchronization with the illumination source. Using the proposed method, multiview displacement spectra of approximately 30,000 points in each image were identified using multiview spectral optical flow imaging, producing the frequency domain images of the deflection shapes required for frequency domain triangulation. Here we can see another deflection shape observed at a different measurement frequency. As spectral optical flow imaging readily produces frequency domain images of the deflection shape by performing the Fourier transform on the image sensor, the post-processing required to produce image-based vibration measurements is minimal compared to conventional approaches. In this table, the processing times per analyzed point required to identify deflection shapes in the observed frequency range using multiview spectral optical flow imaging are compared to a typical digital image correlation measurement. The actual times required, of course, depend on the size of the image subset observed at each grid point and will depend on the implementation, but this result can give us some insight on the relative numerical cost of the post-processing stages of both methods. And here we can see the final result, the operating deflection shapes resulting from the frequency domain triangulation step. At the higher frequency, where the random noise in the image-based measurement is more prominent, we can also see the positive effects of the overdetermined triangulation step in the final result. To conclude, an image-based method of 3D operating deflection shape measurement using a single steel frame camera and multiview spectral optical flow imaging with frequency domain triangulation is proposed. Using a single steel frame camera for image acquisition makes this imaging setup particularly cost-effective. Moving the camera to arbitrary locations, the measurement field of view can be extended to measure full-field 3D operating deflection shapes of specimen with complex geometry. The proposed method utilizes the properties of linear time-invariant structures under stationary excitation by multiview triangulation in the frequency domain, and as spectral optical flow imaging produces frequency domain displacement measurements, post-processing times are significantly reduced compared to conventional methods. Its main limitations are that the observed vibrations must be stationary, and of course, precise control of the illumination source is required to perform spectral optical flow imaging measurements. Thank you for your attention.